In this presentation, we're going to go through waiting inside of TBC when doing a network adjustment. So before going deeper, as a reminder, we need to drag and drop the job files here in TBC. Those are indicated in the Project Explorer and in the Plan View. So next, we are going to go to the Survey ribbon at the top, and then we're going to go and find the Adjust Network icon, and we are going to tap on that. That will open up our dialog box. Then in the lower right-hand corner of the screen, we're going to tap on Adjust. So the software is going to go through a bunch of iterations to try and find the most probable position of where the actual points are. Now you can either have a pass or a fail. So in this example, it's a fail. And so we now need to see if we can pass using weights. So in the weight box, and based on the data you've brought in, you're going to see different boxes that are manipulatable. So here I brought in both total station and GNSS data. And if you look at them, you can actually see them. Now we have three columns. You have reference factor, scale factor, and redundancy. Redundancy relates to just how much of those types you have over and over throughout the whole dataset. So if you look, there is a lot of RTK observation that was done. So we have a lot of redundancy there. But when it comes to total station, there is a lot less information in here. Now, what's interesting, if we look at the azimuth, we have no redundancy, but that makes total sense. Normally, when you set up a total station and you're using an azimuth, you generally just start up with only one azimuth in a project, and then everything else becomes just coordinate based. So why did we fail a chi-square test? So in simple terms, the software is saying that it doesn't believe it can make a judgment call on what's the best position is. But it can help you out by showing you where it believes the actual error is. So how do we know where it is? Well, typically, to pass a chi-square test, reference factor needs to get close to 1. So generally about 0.8, 0.9, 1.1, etc. So in this particular example, let's look at the reference factor and see which one is further away from 1. Well, the answer is the vertical angles. So simply the software is saying, I'm confident on where we think the coordinate is based on these vertical angles. So do you want to apply a scalar that reduces that confidence? And in my opinion, I would just simply say yes. And let's tap on that star and let's loosen things up. And after this, we can just tap adjust. And so you try to go through this in a linear pattern instead of trying to tap every single one of them because you want to see how it displaces the actual error. So before I do that, in the results page, I'm going to tap on point 4. So you can see that we have a coordinate here for this point and the precision that we believe is on that point. And the software is saying, I don't believe this number is really what it is, and I don't believe the precisions are exactly what they are. So would you like to distribute the weight? So we are saying yes, and I've already tapped on it and it's now on the box. So I'm just going to hit the adjust button. And let's now see what the actual precisions, probability, and position of where that point is. So here in the results, we'll see that we will still fail, but the precisions are much lower than before. This is really good data still. But the idea is you've actually distributed more of that uncertainty away. Now we move to the last step. So it's so close to being passed. So which one do you tap? Well, how I think of it is all these are kind of in space where I'm okay with it. I have a lot more redundancy to work with in RTK. So, what I would prefer to do instead is I would prefer at this point to distribute what remains into the large amount of repeatable data sets that I've done checks on. So, I'm going to apply the scalar to this, adjust, and then potentially will hit the required pass mark. There you go. It's 0.95. It hasn't changed in terms of the precision, and the precision is still roughly the same. I've just kind of distributed the remaining errors, right? The remaining large redundant data that I had in my network. So, this is an explanation of how to apply weighting to arrive at the most probable position on where those coordinates are.